Hello, lovely grade 11s. In today's lesson, we're going to be looking at Boyle's law and ideal gases. And without any further ado, let's have a look at this question that we have here. So we have question 5. It says an investigation was done to determine the relationship between volume and pressure of a fixed mass of dry gas. The table below shows the results of the investigation. Then 5.1 says name and state in words the law being investigated here. So we know the law that is being investigated here is Boyle's law. So Boyle's law states that the pressure exerted by an enclosed gas is inversely proportional to the volume it occupies at constant temperature. So a mark for saying it's Boyle's law and 2 marks for stating the definitions of Boyle's law. Then write down an investigative question for this investigation. So a powerful investigative question always has the keyword, what is the relationship? So you mainly say, what is the relationship of the pressure of an enclosed gas and the volume it occupies at constant temperature? So we are still keeping our independent variable pressure, our dependent variable volume, and also our constant variable temperature or control variable. Then 5.3 says, apart from the mass of gas, what other physical quantity must be kept constant during this investigation? So from the definition, we got it that the one that must be kept constant is obviously temperature. Then 5.4 says, use the attached graph paper on page 14 to draw a graph of volume versus pressure for the gas. But unfortunately, we do not have the page 14. So let's just use our whiteboard here to draw. Then down here, we have our independent variable, which is pressure, measured in kilopascals. Then in the y-axis, we have our dependent variable, which is volume, measured in centimeter cube. And then right now, to draw this, we need an interval. So looking at our pressure values, we can see that here we have 3.5 and then 4.25 and then all the way to 25. We can choose to have an interval of 5. So that means here the distance in between our numbers will be 5 units. So that's 15 and then 20 and then it ends at 25. Then in our y-axis, we have 5, and then followed by 10, 15, and then 20, 25, then we have 30, and then ending at 35, right? So this is our y-axis, and this is our x-axis. Then using the values there, you can see that we are given 5 to 25. So 25 to 5, we will plot our value here. And then the second one is 10 to 12.5. So we have 10 to 12.5. So 12.5 would be somewhere here. And then the third one, we have 13 to 10. So where is 13? 13 might be found here and then corresponds with 10. So from this, you can get that the general shape that we're going to have here is this, right? So why are we getting this shape? It's because pressure and volume are inversely proportional. So inversely proportional will end up with a graph like this. So this is the graph for pressure, inversely proportional to volume. So this is pressure is inversely proportional to volume, which is why we get the shape here. So the pressure versus volume graph will always indicate that pressure is inversely proportional to volume. So this is the graph that we draw. And then here our heading will go as pressure versus volume graph, right? So this is pressure versus volume graph. So you have the heading, you have the correct labeling of the axis, and then the shape of the graph is correct. So that should get you all the marks. Then 5.5 says the product of the pressure and volume PV for each reading is approximately constant. show that the unit for PV is the joule, right? So this question here comes from knowing that the SI unit for pressure, we know that the SI unit for pressure is kilopascals, but also Newton per meter square, right? So Newton per meter square is also the SI unit for pressure, but then volume, we know that the SI units for volume are centimeter cube or decimeter cube, but also meter cube is an acceptable SI unit for volume. Now, if we multiply P times V, we would obviously have to multiply the SI units here. So N Newton meter per meter square, and then multiplied by meters cube. Then here, if we are using the fact that M and M are same bases, we can add the exponents, then we'll end up with Newton meter, which this Newton meter is equivalent to a joule, right? So that's how you were just supposed to answer that question there. Then let's proceed. We have a 5.6 says when the pressure is extremely high, the pressure volume relationship deviates from the law referred to in question 5.1. Explain why this deviation occurs. So to explain that, we simply say particles of real gases occupy a volume. At very high pressure, the volume of the gas particles becomes significant, and the measured volume becomes greater than expected. So from what we just identified, we know that pressure is inversely proportional to volume. We expect that at very high pressures, the volume would be very, very low. But then because a real gas in nature occupies a volume, then it cannot go down to it having almost no volume. So at that point, the volume of the gas particles, the real gas particles, they become significant, which opposes what we are expecting as of an ideal gas, because an ideal gas at that point would have no volume, no significant mass. But now this one starts to have a significant volume, which now deviates from the behavior of an ideal gas. So an ideal gas would have no definite volume, no definite mass, but then now a real gas occupies a volume which now deviates from a ideal gas behavior, and therefore there is a deviation of the pressure volume graph, right? And therefore we say the measured volume becomes greater than expected. Now 5.7 says calculate the pressure exerted by the gas when the volume of the gas is increased to 45 centimeter cube. Now we can see that 45 centimeter cube can just be below this 35 here, so 45 centimeter cube. So in this case, we'd be using the values that are just closer to this 45 centimeter cube, meaning we'll take this one as V1 and then take this one as P1. So the 45 centimeter cube would be our V2, and then we are looking for P2, which we do not have, right? So this is the pressure that we are trying to calculate. Now, using our formula, we know the formula for Boyle's law is P1, V1 is equals to P2, V2, right? So what's our P1? We decided to take the 3.50, and then what's our volume? It's 35 centimeter cube. So remember, the pressure in here should be in kilopascals, so it's correct. And the volume in here should be in centimeter cube. So no need for conversions. So P2, and then what's the volume? It's 45 centimeter cube. At this point, we understand that we have to divide both sides by 45. So let's grab our calculator real quick. So we have 3.5 multiplied by 35 divided by 45. And then voila, we get our P2, 2.72 kPa, right? So easy peasy max. Now, let's get to this one. Question 4, it says, the relationship between pressure and volume of an enclosed gas at 25 degrees Celsius is investigated. The results obtained are shown in the table below. Then 4.1, as expected, it says state Boyle's law in weights. So remember, we are doing Boyle's law, so you'll always have to expect to define that. So Boyle's law states that the pressure of an enclosed gas is inversely proportional to the volume it occupies at constant temperature. So make sure that you include enclosed gas. An enclosed gas, the pressure of an enclosed gas is inversely proportional to the volume it occupies at constant temperature. So we must see the independent variable, the dependent variable, and also the controlled variable. So we have 4.2. It says, answer this question on the attached graph paper. And then it says, use the data in the table above to draw a graph of pressure P versus the inverse of the volume 1 over V on the attached graph paper. So right now we must use the values in here and the values there, right? So remember, it's pressure and 1 over V. So let's start by drawing the graph here. We have our graph like that. So remember, down here we have 1 over V, which should be measured in meter per cube. And then here we have pressure, which should be measured in kilopascals. Then here we can choose to have an interval of 50. So that's 0, 50, 100, and then we're going to have 150, and then we're going to have 200, right? Then for the other one, let's see the interval that we can choose. Here we have 8.2, 13.2, 20.6, 23.1, and that. So we can choose to have an interval of 5. So this will be 5, and then 10, 15, 20, 25, and then here we have 30, right? So using our values there, let's just plot a few points. So 50 goes with 8.5. So 50 to 8.5. So 8.5 might be somewhere here. And then we have 80 with 13.5. So 80 might be somewhere here and 13.5 might be somewhere there. Right. And then we have 125, which might be in here, corresponds to 20.6. So 20.6 might be somewhere there. So generally, the graph that we're going to have is a increasing function like that, an increasing straight line, which indicates, so we have to extrapolate it all the way to 0, to the origin. So I'm not using a ruler, so yeah, my line won't be that straight. But then this is the general shape that we have for pressure. This will be kPa and then 1 over V. So basically the idea here is that for pressure versus 1 over V graph, we must have a directly proportional relationship. So here, this indicates to us that we have a directly proportional relationship between these two quantities. So label your axis here. So we have labeling of the axis is correct. This is pressure. This is 1 over V. And then heading, it's correct. And then the shape of the graph, it's in the form of directly proportional. So it's correct. And also your interval here in your graph, correct. So they should earn you all the marks. Then 4.3 says, which physical quantity can be determined from the gradient of the graph? Give a reason for the answer. Now, for the gradient of the graph, we must always know that the quantity that the gradient of the graph represent is temperature, right? So the temperature is always represented by the gradient of the graph. So temperature. So if we check this, this is PV, and then we say PV is equals to T. And then from this, you can see that our volume here is an inverse. So that's 1 over V. And then T is equals to P over V, right? So remember the pressure there was the y-axis, and then V was at the x-axis. This is how we calculate the gradient, change in y over change in x. Now, looking at this equation, you can see that temperature really does give you the gradient of the graph. So the gradient of the graph is represented by P over V, which is equivalent to your temperature. Then 4.4 says it is found that at high pressures, the shape of the graph deviates from that of the graph obtained in question 4, in question 4.2. Explain this deviation. So once again, we have this question. How do we explain? We say particles of real gases occupy a volume. At very high pressure, the volume of the gas particles becomes significant, and the measured volume becomes greater than expected. And therefore, we have a deviation of the real gas to the ideal gas. Then 4.5 says calculate the number of moles of gas present in the sealed container at a pressure of 125 kilopascals, right? So the formula that we have to apply here when we are looking for number of moles is obviously PV is equal to nRT. Now, you know, you do not have to memorize this formula. It will be given in your data sheet, but you do have to know the conditions that apply in you using this formula. So the pressure here should always be given in what? So P is for pressure and should always be given in pascals. And then V is the volume, and the volume in here should always be given in meter cube. And then R is your number of moles, which should always be given in mole. That's what you are looking for. And then R is our constant 8.31 joules. So this is the molar gas constant. And then T is the temperature, which should always be given in kelvins, right? So kelvins. So if they gave you in degrees, to convert degrees Celsius to kelvins, we know that we have to add whatever number that we're given in degrees to 273. So now let's look at the information once again that we are given. We are given 125 kilopascals. So there has to be a conversion that takes place here. And then above here, we are given the temperature, which we can see it's in degrees Celsius. So there's another conversion that needs to take place. But then let's look at 125. When the pressure is 125 kilopascals, what's the volume? So we read that the volume is 0.049. Now, this is the volume that you need to take, not this one. We do not use the value for 1 over V. We use the one for volume in meter cube, right? So 0.049. Then, so that's PV is equal to nRT. The P here should be 125 multiplied by 10 to the exponent of 3. So if we are converting kilopascals, 2 pascals, we multiply by 1,000, right? So the V, we take it as it appears there. What is it? 0.049. So we have the 0.049, and then we are looking for N. The R is 8.31, and then the temperature, there is 25 degrees Celsius. Therefore, we need to say 25 plus 273. This gives us a 298 kelvins. So we substitute it here, 298, right? Then at this point, we have to divide both sides by 8.31, 298. So if in here, divide by 8.31, 298, right? Then if we divide both sides, let's divide and punch all that in the calculator. 125 times 10 to the exponent of 3 multiplied by 0.049 over 8.31 times 298. So this gives us a value of N equals to 2.47 mole, right? So just like that, we have calculated our number of moles. And how many marks was that? Let's check. 4 marks. Okay, so now let's look at another question here. We have question 7. It says the graph below represents the relationship between the pressure and the volume of oxygen gas at constant temperature. Now, again, 7.1 says state Boyle's law in words, right? So we already know what it is. Then Boyle's law states that the pressure of an enclosed gas is inversely proportional to the volume it occupies at constant temperature. Do not be lazy to write it over and over again, because that's how you make sure that you never forget it. Then 7.2 says, write down the mathematical expression in symbols for the relationship between the variables on the graph. Now, we already know the relationship between pressure and volume is what? Inversely proportional. So in answering our 7.2, we'll just say pressure is inversely proportional to volume, right? So that's the mathematical symbol, pressure inversely proportional to volume. So that means the greater the pressure, the lower the volume. 7.3 says, write down two variables that must be kept constant during this investigation. We have already discussed one of the variable that must be kept constant is temperature, but also number of moles as well, right? From this equation here, nRT, we get that what must be kept constant is the number of moles and also the temperature. So if you ever forget it, just look at this formula here and know that the ones that you have on your right here are the controlled variables, the number of moles and also the temperature. Then 7.4 says, define the pressure exerted by a gas. What is the definition of pressure? So simply, pressure of a gas is the collision of the molecules with the walls of the container. So that's what pressure is, the collision of the molecules with the walls of the container. Then 7.5 says, calculate the pressure in kilopascals exerted on the gas when it is compressed to 5 dm cube. So right here, we can see that our volume has been given with the SI unit dm cube and our pressure kilopascals. Now, if we are looking to calculate for the one whereby they say 5 dm cube, can predict that 5 dm cube is somewhere here. So the pressure that we are looking for must be somewhere there, right? So this is using these values, because these values are the ones that come before this pressure here. We can say this will be our V1 and it will correspond to our P1. So we'll be using these values here. And then that means what we have here, the 5 dm cube, will be our V2. And then what we are looking for would be the P2, right? Now, there are two ways in which we can calculate this. We can use these values 90 and 3, or we can use the 45 and the 6 here, right? So, but then now let's calculate with the 90 and 3, and then we'll also calculate with the 45 and 6 just to prove that we're going to get the same value. So the formula that we're going to use is P1 V1 is equals to P2 V2. Now, our case, the P1 is, we said, is the 90, so it's 90 kilopascals. Now we know we must convert that one, so it's 90 times 10 to the exponent of, it should be in kilopascals. We do not convert for this one, it should be in kilopascals. Remember, it's the P1 V1 formula. So here the pressure, yes, should be in kilopascals, but the volume is the one that needs to be converted. It needs to be in centimeter cube, right? So we have the 90, and then this corresponds to a volume of 3 dm cube. So we need to say here for this one, that's 3 times 10 to the exponent of 3, and then it's equals to P2. That's what we are looking for. But they told us that it increases to a pressure of 5 times 10 to the exponent of 3, right? Now, at this point, we have to divide both sides by 5 times 10 to the exponent of 3, like that. And then the P2, let's quickly use our calculator. So we have 90 multiplied by 3 times 10 to the exponent of 3 over 5 times 10 to the exponent of negative 3. That will give us a pressure of 54 kilopascals. So yes, we were required to calculate it in kilopascals, right? Then as we are told here, then okay, now if we had to calculate using these values now, let's erase here and let me show you how you do that. In this case here, you would say, in this case here, you then say, okay, this is still my 5d cube. But then right now, because this volume is coming before the 6, so this is 5. So this would be V1, and it will correspond to the P1, which you don't have. But now you'd have the V2 here, and then it corresponds to the P2, right? So now they're saying calculate the pressure in kPa exerted on the gas when it is compressed to 5 dm cube, right? Or either way, even if you can say this is V1, V2, it still doesn't change anything, right? Still doesn't change anything. So we're going to have P1, V1 is equals to P2, V2, right? So the P1 in this case is what we don't have, but we have the volume 5 times 10 to the exponent of 3 is equals to P2 is, in this case now, it's the P2 that you have is 45. And then here we have 6 times 10 to the exponent of 3, right? And then at this point, again, divide both sides by 5 times 10 to the exponent of 3. 5 times 10 to the exponent of 3. When you do this one, still your pressure will be 54 kilopascals. So either way, you're still going to have the same value. Now, 7.6 says, state the conditions under which real gases approach. So look at this. This question comes in two different ways. They can say state the condition under which real gases approach the ideal gas behavior, or they can say state the condition under which real gases deviate from ideal gas behavior. Now, I'm just going to answer both of these questions. Now, I'm going to start by answering this by when will it deviate, right? So the case is when it will deviate. Before we reach approach, let's answer when will it deviate. This will deviate, and a real gas will deviate from ideal gas behavior when there's low temperature and high pressure, meaning it will approach real gas behavior when there's what? High temperature and what? Low pressure, right? So in order for a real gas to approach ideal gas behavior, there needs to be high temperature. 7.7 says tabulate the difference between ideal gas and real gases, right? So we're just going to go ahead and tabulate that. So we say for real gases, make sure, guys, you know this table, study this table here. Real gases, we say particles have a definite volume and mass, but with ideal gases, particles do not have a definite volume and mass. Then for real gases, collisions between particles are inelastic, right? So that means here there is loss of what? There is loss of kinetic energy in this one, right? Then, but here collisions are what? Are elastic. So that means no loss of kinetic energy. And then the kinetic energy changes with collision. But here, the kinetic energy of particles will remain constant because remember, there is no loss of kinetic energy. Then here, for the real gases, there are intermolecular forces between particles. But then for ideal gases, there are no intermolecular forces between particles, which is why an ideal gas will always obey all the gas laws under all conditions of pressure and temperature, right? So it's always like that. Then an ideal gas, you have to remember that an ideal gas is just a theoretical gas, right? So this is not a gas that actually exists in real life. This is a gas that we just use to compare or to rather give an idea of how a gas should actually look like, how a perfect gas should actually look like. But remember, there is no such thing as a perfect gas. We have real gases that can have a definite volume and mass, and then that have intermolecular forces that have change in kinetic energies, and whereby the particles and the collisions in the particles are inelastic, right? So, yep. Then 7.8 says, give a reason why oxygen gas deviates from ideal gas behavior at low temperatures. So I think I've already explained a bit about that. We say at low temperatures, the kinetic energy of particles is very low, right? So the kinetic, remember, when we speak of temperature, we are simply speaking. So temperature, by definition, we say temperature is the average kinetic energy of particles. So average kinetic energy of particles. So when we speak of temperature, we are actually speaking about the kinetic energy of particles. So at low temperature, the kinetic energy of particles is very low. So low temperature, low kinetic energy, or slow or lower kinetic energy, yes. And then this allows intermolecular forces to now exist between the particles. But now we know once there are intermolecular forces between the particles, then your real gas will start to deviate from an ideal gas, because remember, an ideal gas does not have any intermolecular forces in between its particles. So the existence of intermolecular forces in real gases makes the real gas to deviate from ideal gas behavior. So, okay, then now let's go to question 5. It says in 1783, Jacques Charles filled an air balloon with 2,600 grams of diatomic gas X. So this is a diatomic gas that we don't know of. Then the pressure of the gas was 100 times 10 to the exponent of 10 to the 100 times 10 to the exponent of 3 pascals. So this is given in pascals at a temperature of 23 degrees Celsius. We know that our temperature should be in kelvins. So there's conversion that will take place here. And it occupied a volume of 31.98 meter cube. So this volume here is in meter cube. So we know that it is in the correct SI unit. Then 5.1 says, give the term of a gas that obeys the general gas equation PV is equals to KT under all pressure and temperature conditions. So we just spoke about that. We said an ideal gas will obey the gas laws at all conditions of pressure and temperature, right? Then 5.1, we say that's an ideal gas, ideal gas. Then 5.2 says determined by calculation the formula of the gas, and that is a lucrative 7 marks, right? So we do not Dazel. So let's do our question, our 5.2 for 7 marks. So we know the formula that has to apply PV is equals to nRT, right? So what is our pressure? Our pressure should be given in pascals, which is in the correct SI unit. That's 100 times 10 to the exponent of 3. And our volume should be given in meter cube, which is in the correct SI unit, 31.98. So we have 31.98. And then we are looking for N. Remember, to get to the molar mass, to get to the formula of the gas, we have to calculate its molar mass and therefore find its molecular formula. So the best way to get to the molecular mass is to start by calculating the number of moles, because we saw that we are given 2,600 grams, which is the mass. So after here, the formula that we have to use is N is equals to M over big M. We do have the mass. We would have calculated the number of moles from here, and then we are looking for the molar mass so that we can have the molecular formula, right? Then R is 8.31, but the temperature, we do not substitute the 23 here. Remember, the temperature must be in kelvins, so that's 23 plus 273. So you always note that, guys, that we do not substitute in degrees Celsius. So this will give us 296 kelvins, right? So that's what we're going to substitute in there. And then we have 296 here. And then if we divide both sides by 8.31, and then 296. Also here, divide 8.31 times 296. So here we do understand that this will cancel out. And then let's punch this in our calculator. So we have 100 times 10 to the exponent of 3 multiplied by 31.98, then over 8.31 times 296, right? So this will give us number of moles of 1,300, right? 0.13 grams. Then let's use this one to calculate. Let's use this one now to calculate the formula of the mass, right? So we are given 2,600 grams here. So this will be N is equals to M over big M. So we have our number of moles. And then to calculate the molar mass, we can say M over N here. So this will give us 2,600 divided by 1,003.13. So let's check. We have 2,600 divided by 1,003.13. This gives us the molar mass is 1.9998, which is just approximately 2 grams per mole, right? So we can just round it off to 2 grams per mole. Now remember, they said X is what? A diatomic gas, right? So this is a diatomic molecule or a diatomic gas, right? Then we know that a diatomic gas that would have a molar mass of 2 grams per mole is obviously H2, right? Because remember, H has a molar mass of 1. If there are 2, then we'll say 2 times 1. This will give us 2 grams per mole. So it's because they said diatomic. So we do understand that helium also has what? 2 grams per mole. But then here the keyword was diatomic. So this is why we chose hydrogen gas. So remember, helium cannot be a diatomic gas. And you do not have something like this. There is no he. There is no he. Then, okay. Question 5 says the reaction between calcium hydride and water is often used to inflate weather balloons. The reaction produces hydrogen gas according to the following balanced equation. Then 5.1, 8 marks, says calculate the mass of calcium hydride needed to generate 53.3 dm cube. Conversion needed because we want it in meter cube. So what do we do? dm cube to meter cube, you multiply it by 8,000. So times 10 to the exponent of 3. And then of hydrogen gas at a pressure of 108 kilopascals and a temperature of 21 degrees Celsius. So again, another conversion here, plus 273. And then also 108 kilopascals, another conversion here. So we multiply that by 10 to the exponent of positive 3. Oh, this one, it's times 10 to the exponent of negative. Let's fix this one quickly. So this one should be times 10 to the exponent of negative 3. When we are converting dm cube to meter cube, we divide. So this is more like dividing by 1,000, right? So, okay, now let's get down to that. So it's PV is equals to nRT. First, we have 108. So this is 108 multiplied by 10 to the exponent of 3. And then my volume, they gave me 53.3. But then what am I going to do? 53.3 times 10 to the exponent of negative 3. So that's divide by 1,000 is equals to N. Then my R is 8.31. But my temperature, I will now have that 21 plus 273. So that's 21 plus 273. This will give us 294. So we have 294. Divide both sides by 8,31. So you can see with applying this formula, we are always doing one and the same thing here. You can almost see the calculations that we are performing, that they do not ever change. Then we have this 108 times 10 to the exponent of 3. Then multiply that by 53.3 times 10 to the exponent of negative 3. Then divide by 8,31 times 294. This will give us number of moles of 2.36 mole, right? So now when we have this, remember what we are looking for is the mass, right? We are looking for the mass of calcium hydride. But look, they said calculate the mass of calcium hydride needed to generate 53.3 dm cube of what? Of hydrogen gas. So the number of moles that we just calculated here are for the hydrogen gas. And another thing that should hint you in terms of us having to calculate the number of moles of hydrogen gas is that hydrogen gas here is the only one that is in gaseous state, right? So remember, pressure only applies to gases. So pressure is for gases only, right? So the pressure does not apply to aqueous molecules or the ones that are in liquid or solid. Pressure only applies to gaseous molecules. So this one, we just calculated the number of moles of hydrogen gas, but then we are looking for the mass of calcium hydride. Now we know to get to that part, we need to use ratios. So we say ratio of hydrogen gas to calcium hydride is what? 2:1. Where do I get the 2:1? I say the coefficient of hydrogen gas is 2, but the coefficient of calcium hydride is 1, right? But then remember, I just calculated the number of moles of hydrogen gas. So beneath the ratio of hydrogen gas, I put 2.36, and then here I have x. If I cross multiply here, this is 2x, and then 2.36. Divide both sides by 2, then my x is equal to, let's punch that. So we have 2.36 divided by 2. This will give me 1.18. So that's 1.18 gram. So guys, always make sure that you punch in your calculator. Do not try to be the maths John Wick or maths Steven Seagal. You know there's a lot of mistakes that you can make from just wanting to calculate using your head. Then we have this. Oh, it's mole, not grams, mole. And then now we are looking for the mass. So it's N is equals to M over big M. Then mass is N times M. So the number of moles for calcium hydride is 1.18 multiplied by the molar mass. So we have 40 plus 2. So that's 42 times 1.18. So this gives us a value of 49.56 grams, right? So that's your mass. That's your mass. That's your mass for calcium hydride. Then let's check. 5.2 says, how will the answer to question 5.1 change if the same volume of gas is produced at the same pressure but at a lower temperature? Right, same, right? So for this one, what will be our solution? It will be increase. Now let's check why we are saying increase. So this is PV is equals to nRT. Now if we decide to make the number of moles the subject of the formula here, this will be N is equals to PV over RT, because we'll just divide out by RT. And then now look at the relationship between the number of moles and temperature. So number of moles and temperature are inversely proportional. They just spoke about lowering the temperature. So this means it will increase the number of moles. So a lower temperature results in an increase in number of moles. But then this does not answer the question for the mass, right? Because we were calculating the mass. The form, whatever that they're asking us about in 5.1 is the mass, right? Now, how do we link this number of moles to the mass? We know that the number of moles is directly proportional to the mass. So if the number of moles are increasing here as a result of a decrease in temperature, that means also the mass will increase, because number of moles and mass, they are directly proportional. So an increase in number of moles will result in an increase in the mass, which is what they asked about here. They said, how will it affect the value that we calculated in 5.1? The value that we calculated in 5.1 was the mass. So that means now, if we lower the temperature, the mass will then increase, right? So I hope it all makes sense. So guys, keep on practicing. This is a very easy topic. Collect marks in this topic, and do not forget to subscribe to the channel so that I can give you more of this content lessons. And guys, hit that like button, and then also comment on the comment section below if you like these lessons.